So today also, right?
Yeah, we'll talk about the DSC. We'll finish this topic, DSC. We just talked. So we talked about this binary weighted DSC, right? Binary weighted DSC. And before that, we talked about the step size in details, the step size, the resolution, and the resolution of the step size equation. Just small recap from our previous lecture. So we saw that this resolution is equals to your reference voltage divided by the 2 to the power n, where n is the number of bits. So if you want to represent, so we are trying to get digital to analog converter. That means your input, if your input bits considered with 3 bits, that means number of bits equals to 3, so it will be n equals to 3. If you represent your DSC, consider 4 bits, 2 to the power 4, like that. Okay. And then we also discuss about the full scale output voltage, FSO, full scale output voltage. And the equation was 2 to the power n minus 1 times Vref by 2 to the power n. So as you can see, this is the resolution, or this is also known as step size as well. Same thing. Or 1 LSB, everything is same. So this FSO is actually 2 to the power n minus 1 times step size. 2 to the power n minus 1 times step size. Or we can say this step size equals to full scale output voltage divided by 2 to the power n minus 1. So these are the few equations we can keep in mind so that we can solve our problems. Okay. So in a binary weighted resistor, we choose the resistor value inversely proportional to the binary positions of the bit, right? Binary positions of the bit. And here, I just have, I'm voting for one of, will it come today or not, I don't know. So I'll go to the board again just to discuss a few things here. We have 2 questions in our last lectures. One is the question from you, why the resistor value, we cannot choose the random value, right? You asked me the questions. So the binary weighted DSC has a few drawbacks. This one. So here, in a binary weighted digital to analog converter, resistor values are chosen according to the weight of each binary positions to ensure the output voltage accurately represents the digital input. So because we have to represent accurately 1 0 1 1 0 1 1, so the bit position will decide the value, the weight. That's why we need to maintain the R value that we are choosing the resistor value in the binary weighted. So this was the binary weighted, right? For example, this one. Then we give it to the open summing amplifier, right? So the value of this resistor will be inversely proportional to the binary weight. Why? So that we can represent accurately the digital input with each bit contributing a value proportional to its weight. So that was the reason. Another important question was asked, but he is not here today. He was telling me what happened. So we found that this during the quantization error, right? whenever we do this DAC, we found that there is some quantization error every time. And he asked me, we can minimize that error, minimize this quantization error if we change the input voltage. So here we give some input voltage here. So if it will be connected either to the ground or to the reference voltage, right? It is connected to either to the V reference voltage or V in and or to the ground. So for example, V reference was 3.3 volt, and we saw that it was is a 3 equivalent to 3 is 0.11, right? So there is 0.3 volt quantization error. Then he told me that if we can minimize by changing the input voltage, so that is also possible. This is known as dithering. You can see here. So to reduce the quantization error, there are 3 steps we already discussed. One is the increasing the ADC resolution. That means you can increase the number of bits. At first we have 3 bits, then we can increase to 4 bits, 5 bits. We can increase the number of bits, we can increase the resolution, reduce the step size, we can minimize the error. But if you keep increasing your number of bits, that means bandwidth will increase. Okay, but that is the option. Another option is oversampling. What is that oversampling? When you talk about the sampling theorem, there are 2 things. Right? One is undersampling. Omega s should be less than twice of omega n, right? Omega s less than twice of omega n. This is undersampling. So if this is undersampling, we cannot recover our original signal. Then we saw that omega is equals to twice of omega n. This is the Nyquist rate. Usually we follow this Nyquist rate. Another thing is we call oversampling. Omega s is greater than twice of omega n, the band gap, right? Sorry, guard band. So if we can remember our circuit here, the waveform or the, so this was omega s, this is omega m, this was minus omega s. So this is twice omega s, this is the gap. So if we maintain this one, it is the oversampling. Omega s should be greater than or equals to twice of omega m. And if they are equal, then this line will be like this. There is no overlapping. When omega s equals to twice of omega m. So if you take this oversampling, then also we can minimize this quantization error, because now we are taking more area. That means the error are spreading more area. So they mentioned that oversampling involves taking more samples of the input signal per cycle. We are taking more samples now. And then the Nyquist rate, this spreads the quantization noise over the wider frequency. So it will spread the quantization error to the wider frequency band, making it easier to filter out and reducing the perceived noise. The third one is the dithering that he mentioned, that we can change our input signal. I think you have a question.
Yes. What's the omega s equal to 2 omega m? What is called?
So this is the sampling frequency, and this is the maximum message frequency. So omega is in radian per second, and if you just convert it to frequency, omega equals to 2 pi r. Okay.
And
so this is the
what is the state is
frequency.
called? If they are equal, what is the state called?
So then Nyquist rate. Nyquist rate. When they are equal, we call it Nyquist rate. This is the minimum requirement for sampling. Otherwise, it will be overlapping. We cannot recover our message signal. Okay. So dithering is the important one. So that what is the dithering? It mentioned that dithering adds a small amount of control noise. That means this is a noise actually. This is not your signal. If there is anything other than signal, we consider as a noise. For example, we just consider so we round up at for example 3.5. So we just consider 0.2. We just add it. So this 0.2 volt is actually a noise, but we can add those things. So that portion is known as dithering. Dithering adds a small amount of control noise to the input signal before the quantization. And this noise helps to randomize the quantization error, making less noticeable and reducing the potential for the harmonic distortion.
The question is, why we are adding more
This is the options. So whenever he asks me a question, then I was also not think like in that perspective. Then I try to find out, yeah, it's possible. So that means two quantization arrows. So that means it is a control noise. That means you already know. You added 0.2.
Oh.
So on the receiving end, you can then subtract that 0.2 also.
Okay.
So this is in your hand. Here's a control one. So but this technique is known as
Deterring. Okay.
Okay. So this is the few questions we found from our previous lecture. Then we also mentioned about this, how we can do this low pass filtering, then what is the quantization error. I will upload this word file. Now let's go through this.
I have one more question.
Yeah, sure.
Last time we draw this circuit. Is this kind of circuit we need to draw in the exam?
Yeah. So the question will be like this: convert this signal by using a binary weighted, 3-bit binary weighted. So you have to draw the circuit, then you have to calculate the output voltage. The input will be given, input code is given, for example, 1011. So if it is a 1011, that means it's a 4-bit binary code. So you have to give the 4 register value. So you have to draw 4 register. Then you have to decide which is the MSB and which one is LSB.
LSB.
Then the MSB will have the lowest resistance, the LSB will have the highest resistance value.
Isn't it the resistance should be same?
No. The resistance should be same for which one? It is ADC.
ADC, yes.
Flash ADC. It was the flash ADC, not the DAC circuit.
Yeah, we studied the flash ADC before.
So in case of binary weighted DAC, whenever you calculate this output voltage, the equation was, so okay, let me draw this. I'm sorry, I just removed this. So this was our circuit. So we give that to the inverted port. This is RF. This is my V out. And here we give the reference voltage. This is my grounding. And this is what the reference voltage is. So if there is a mechanical switch or microcontroller switch, we just turn on and turn off. We can, depending on the bits, we can just make it either 5 volt or 0 volt, right? Okay. So what is the V out equation? The V out is equal to, as we have the inverting amplifier, it's a negative sign, so it will be minus IF times RF, or we can say minus RF times V reference into V2 by R plus V1 by twice R, V0 by 4R. Right? So V2, V1, V0, LSB, and this is the MSB. So if you have 4 bits, it will be R twice R, 4R, 8R, like this. So if the inputs and the weight of each resistor is according to the binary number, then it can be used to convert the digital input bits into the analog output voltage. So did we do any example last time? We have done one example, I think, right? So in the example, in your exam also, you have to compute this calculation. So the reference voltage will be given, the input code will be given, you have to find out the full scale output voltage and the equivalent voltage, okay, and the equivalent voltage. So for example, here we already saw one more thing. This RF and the feedback resistor is equals to R, So for example, it is R twice R, 4R, sorry. So this RF equals to R. Okay. And reference voltage, B reference voltage is given equals to 5 volt. And the digital input code is given, for example, 101. You have to find out the output voltage, calculate the output voltage, or find out the output voltage, and also find out the full scale output voltage. So what does it mean, full scale output voltage? The full scale output voltage means when all the bits are 1. when all the bits are 1, that means 1, 1, 1. Then what will be your output voltage? That is known as full scale output voltage. And whatever the 4, we have to find out the equivalent output voltage. So at first, if we try to find out the equivalent output voltage, we already know the equation. Equivalent output voltage V0 is equals to minus RF times V reference. We have our equation V2 by R, V1 by twice R, and V0 by 4R, right? So already given RF equals to R, so we can write down this is just R, and V reference is given 5 volt. Now, what is my digital input code? 101. So it will be 0, it will be 1, so 1 over R. Or if you take the common R here, then 1 plus 0 plus 1 over 4. Let me write it properly. So this is R times the reference, then I take common 1 over R here. So then this R and R will cancel easily. This V reference is given 5 volt. And this is 1, this is 0, this is 1 over 4.
How did we get 1 over R?
Oh, so here R.
Oh, okay.
So we take a common question. So if I go very fast, let me know, okay? If you don't understand, just please let me know. So this is our general equation. V2 by R, V1 by twice R, V0 by 4R. This is for 3 bits. For 4 bits, it will increase. Then it will be V3 by R, V2 by twice R, V1 by 4R, V0 by 8R. So it will keep increasing, okay? So in the equation, in the example, they have given that RF and equals to R. That means they are equal. 1 kilo ohm, both are 1 kilo ohm, or both are 2 kilo ohm. And the reference voltage is also given. So you can just put, instead of R, we put R, the reference voltage 5 volt, and now we take a common R here, 1 over R here. According to the bit 101, so it will be 1 plus 0 plus 1 over 4. So if you calculate it, you will found how much? V0 equals to
minus 625.
Yeah, original is 65.
Minus 6.
Just I want to write one more lines, then I'm coming to your point. 5 by 4 equals to minus 6.254. So, if you, whenever we last time, we had this kind of chart, I hope you can remember. In this chart, we can see for this 101, it was equivalent to 25 over 8. But here it is 25 over 4. 25 over 4. 5 times 5 divided by 4, right? 25 over 4. That means this has some internal gain. This circuit has some internal gain. That we also discussed. So that means in such DAC, if RF is equals to R, that means it has some internal gain.
I think you discussed this
Yeah.
previously.
Okay? So we already discussed these things. Okay. Now, so what will be the full scale output voltage? What will be the full scale output voltage? So in the full scale output voltage, if you have to calculate, that means all are 1, right? So that means 1 plus 1 over 2 plus 1 over 4. That means it will become how much? 4 plus 2 plus 1, 7, right? 7 by 4 into 5. That means 35 by 4. So it will be around.
875.
Did I make mistake?
5 by 8.
875.
8.7.
Oh, the total output, final output, yeah. 8.75. So this is the full scale output voltage.
Full
So
scale,
here
okay.
also we can see that though our input reference voltage is 5 volt, but still we are getting 8.75 volt. That means some gain is there. Some gain is there. Some voltage drop across the resistance. Okay.
I have a question.
Yes, please.
I know I've studied it's in the basics of gain voltage and gain loss. The thing is, we're getting negative, right? So if
This
you want
negative means the phase shift, only the phase.
phase shift,
Only the phase.
then
Whatever
if
the
we
input
if we
signal-
put an inverter, then we can get the.
So if you, instead of this one, if you give input to this positive terminal of the
Yeah.
op amp, it will give you the same phase.
Okay.
Yes. We can also calculate the current, right? This is the voltage. Same way, we can also calculate the current of the circuit. So if you want to calculate the current, so here we can consider this is I. So I just want to make sure the same thing here that we in my paper. So I1. So here I1, I2, and I3. So here we'll have the B2, B1, B0. This is my reference voltage and this is my grounding. Okay. So then here we'll get some current I. So we can say the summation I will be equals to I1 plus I2 plus I3. So what is I? I equals to V over R, right? So we can write down V reference by R times same V2 by, or just to mention 2 to the power 0, V1 by 2 to the power 1, V0 by 2 to the power 2. So we can write down this one, R equals to V ref by R times summation of I equals to 0 to n minus 1 b by 2 to the power n minus 1 minus I. So here I is the position of the bits, n is the number of bits. So this is how we can also calculate the current of the circuit as well as the voltage. The amount will be the same. So if I ask you, try to design a 6-bit DAC, binary weighted DAC, just design.
Just that circuit?
Yeah, for 6-bit.
6.
Design a 6-bit binary weighted DAC circuit.
Then we need to have 6 resistor.
Yeah, then try yourself, I'll give you the answer in 2 minutes, then match your results. Design a 6-bit binary weighted DAC circuit. Yeah?
Any input you have?
No, just design it first. Design a 6-bit binary weighted DAC circuit.
Professor.
So what is the R value? If you start from here or start here, if you start from here,
R 2R, 4R, 8R, 16R, 32R.
right? Everyone has the same? Okay. So which one is B naught then?
Wait. B not.
B1, B2,
Yeah,
B3,
no, it starts from the
B4,
yeah.
B5.
So B1, you would still have B1.
B5, right?
So this is how we can design. Okay.
And
Now if I
this
ask,
will be only RF, right?
yeah, alright, prepare. So now if we ask you to find out the full scale output voltage, when the B reference voltage is 5 volt,
5
RF
volt.
equals to R, find the full scale output voltage when B reference equals to 5 volt and RF is equals to R. How much? Minus 9.84375. Right? We have the same equation that V naught equals to be referenced by R times V naught by 16. So we have this same equation. V ref by R times then V5 by 2 to the power 0, V4 2 to the power 1, V3 2 to the power, V3 2 to the power 2, like this, then you can explain. So this is the, also sometimes it will call full scale output voltage, sometimes they will ask you to find out the maximum output voltage. So this is the maximum voltage that can get out at the output side.
So
Dmax.
in
also.
FOS, the equation.
Full scale output voltage.
Yes. In N we need to put the 6, right?
So here you can see how many bits? 1, 2, 3,
3, 4, 5, 6.
Yeah.
6.
So you can equation. You can put that full scale output voltage equation also. You can find it. What will be the minimum input voltage? Sorry, minimum output voltage.
0.
Anything else? Minimum output voltage will be the 1 LSB. 0 means you are not working anything, right? So if you have the 1, minimum 001, the minimum 1 LSB, that the minimum step size will give you the minimum voltage.
That means it is going through
So
32R.
Minimum voltage 1 LSB for the step size is equals to how much? FSO divided by 2 to the power n minus 1. So we already have the FSO value here, minus 9.84375 to the power 6 minus 1. It will give you how much? 0.15625. In a sense that if you don't have any input, then there's a 0 output voltage. But if you have the minimum change, whenever you have the 1 LSB change, right?
If the input
Then,
was all zeros, then you'd have 0 volts.
sorry?
If you had the input all zeros, then you'd have 0 volts.
Yes, then it will be 0 volt. The minimum output voltage means, I just want to mention that if it is minimum 1 LSB change of the step size. Sometimes they can ask you question differently in the papers when you discuss. They will mention in different way, in different perspective.
So for minimum we consider as
So
0, 0.
as he said, that is also true. Whenever all are zeros, then we get the minimum zero voltage. The minimum step size, you can say this is the proper term will be the step size, or the proper term is the resolution, or the proper term is 1 LSB. Or we can say the minimum, sometimes they said that minimum input voltage is some voltage, it's not zero. That means they are actually regarding or corresponding to the 1 LSB. Okay. So we can see that if we increase the number of bits, the value of resistance is increasing in the power of 2, right? 2 to the power n. So for example, for a 10-bit DAC, it required around 512 kilo ohm resistance. If we just think that R equals to 1 kilo ohm, R equals to 1 kilo ohm, the minimum 1 kilo ohm, then for a 10-bit DAC, it requires 512 kilo ohm resistance. That means you need to precise every time. You have to decide precise resistance value. So it is not always possible. That's why to overcome these things, we have another technique for DAC is known as R2R ladder circuit. R2R ladder circuit. It is also known as a resistive ladder circuit. So here the problem is we need a very precise value of resistor, so many resistors. If you keep increasing your number of bits, you need more higher value of resistors, and that should be in the power of 2. So it is not always possible to have the exact value of the resistance, right? So if we can reduce the variation of this resistor, it will be better. So this is the technique where we can get the design only by using 2 different kind of resistor. That's why it is known as R2R ladder circuit. R2R ladder circuit. This is also known as resistive ladder circuit. It is also known as resistive ladder circuit. Let me draw the circuit first, then we will discuss and calculate. The circuit consists of only 2 different kind of resistors. One is R and another is 2R. Okay. So let me design a 3-bit R2R ladder circuit. A 3-bit R2R ladder circuit. This is the circuit. Not complete yet, but this is the resistance. Now we have to give the resistance value according to the input. Here, this resistance will be always twice up, and it will be connected to the ground. Now, as I mentioned that it is a 3-bit R2R ladder circuit, these 3 bits will be given through these resistors, and these resistors are all twice up. That means we will give the digital inputs through this 2R resistor. Okay, through this 2R resistor. For example, if we have, so this is my input, this is the reference, this is my input. Otherwise, they are just grounded. For example, this is grounded. And we have some mechanical switch to connect with this one whenever there is some things.
Is it not like
And these 2 resistors are R.
the first one is also R?
No. This is the thing we need to keep in mind. The first one will be also 2R. So 2R, 2R, R, 2R, 2R, R, 2R. 1, 2, 3. Yeah. Now if you consider this one is B0, LSB, B1, B2. This is LSB, this is LSB. Whenever there is an input, the reference voltage, for example 5 volt or 10 volt, whatever it is, it will connect here. If it is not 1, it will be connected to 0. Either 1, so because logic 1, we can just consider any volt, 5 volt, 2 volt, something, we'll see later. And for logic 0, it is 0 volt. Yeah. So as this is a 3-bit, it can be 1, 0, 0, it can be 0, 1, 0, it can be 0, 0, 1, something like that. So this is the circuit. At first we need to know how to draw the circuit. So this is for 3-bit. If we have a 4-bit, then we have another 2R resistor here. Okay. So how we can calculate the impedance here? We have to calculate the impedance here from here. So this is my input side. So we have to look from here. We have to calculate always from the output impedance of the circuit. Looking from here. We can calculate this impedance voltage by using our Thevenin's equivalent theorem. Thevenin's circuit. Thevenin's circuit. And whenever we apply the Thevenin's circuit, so in the Thevenin's circuit, we actually try to calculate two things, right? One is the Thevenin's equivalent resistance, another is the Thevenin's equivalent voltage, RTH and the VTH. Okay. Let's first see the value of RTH for this circuit, the Thevenin equivalent resistance here. Thevenin equivalent resistance here. So for the Thevenin's equivalent resistance, if you try to find out the resistance, we need to connect all the sources to the ground, right? All the connected source to the ground. That means this is grounded, this is grounded, this is grounded. And here it is already grounded. So when everything is grounded, so if we just started from here, we have to reach here because we are looking from this side. We can see these 2R and these 2R resistors are in parallel. Because you can see, if you look at this node, from this node, this resistance to AC ground. From this node, this is also ground. So these two are parallel. So twice R parallel, twice R will give you what? R. So we can remove this one and we can say we have now R resistance. Right? Now we are moving here. So R plus R, these two resistors are again in series now. So in series means
2R.
R plus R, 2R. So we can remove this one, we can get this 2R. Now again, this 2R and 2R again parallel. So 2R and 2R will give you
R.
R. So we get the R here. Again, these two are in series, so it will give you 2R. Now finally, these 2R and 2R in parallel, it will give you
R.
So this is the beauty of this circuit. Whatever the number of bits, if we keep increasing the number of bits, every time the equivalent resistance will be equals to R. The Thevenin's equivalent resistance will be finally only R. If it is 3 bits, if it is 4 bits, if it is 5 bits, if it is even 10 bits, the Thevenin equivalent resistance will always be R.
If we follow the R to R ladder circuit.
Yes. Okay? Fine. So in this type of DAC, the output impedance is always R. The output impedance is always R, regardless of number of bits. Now these two resistors are connected either to the reference voltage or the ground, right? We already saw. So if I again draw this one, we have here, we have here, 3, right? 2R, 2R, and 2R. Twice R, R, So these two resistors will connect either reference voltage or to the ground, depending on our input code. So the output of the ladder network will depend on the position of the switches, means whether the two resistors are connected in V reference or the ground. Now, the entire ladder network can be represented by the Thevenin entire network. This is a ladder, right? This is called ladder. You can see this is something like a ladder, right? That's why it is known as resistive ladder circuit. This entire ladder circuit we can draw with an equivalent circuit. Like this. So this is RTH. Now we need to find out the Thevenin voltage. We already get this RTH, right? See, we can replace whole circuit with this RTH, but we have to have some details there. So we have to find out the Thevenin's equivalent voltage now. Okay. So to find the Thevenin equivalent voltage, we will consider one voltage source at a time. What does it mean? So here we are trying to understand with 3 bits, right? With 3 bits. This is this was my MSB, right? So this was B2, this is B1, this is B0. As I mentioned, whenever there is an input, it will connect to the reference voltage. So whenever the input, so for example, we have 1, 1, 1. So we have 3 sources, but we will try to consider one source at a time. We'll take one source at a time, we'll calculate, then we'll take to the next, then third. Then we apply the superposition theorem to get the final voltage at that terminal, at this node. Okay, let's see one by one. It will be easy for you. Okay. So for example, should I use this one? This one is better. Okay. So let me remove these things. So we have B2, B1, B0, right? So for example, we have this code. Okay, we have this code 001. So 001 means what? This is 0. So that means this will connect to reference voltage. This is connected to the ground, this is connected to the ground, because we have 1, 0, 0. Okay? So if it is like that, we have to calculate the Thevenin's voltage for this circuit starting from here. See, look at here. You look at here from this side. We can draw the circuit like this. This is twice R, this is twice R, this is the reference voltage, right? Can I draw this one like Zara, can you see? Is it okay? Oh, we should draw that side. Let me draw here. So now we are looking only this portion, this circle portion, okay? This portion. So what is my circuit, equivalent circuit for this portion only? Twice R, V reference, right?
The other
Because we just connected, because this is 1, 0, 0. Because my B0 equals to 1. The LSB equals to 1. So this will connect, this switch will connect to the reference voltage. This connected to the ground, this connected to the ground. Now I am focusing only here, this portion. You can see the dotted line. The dotted line. So dotted line is connected from what? B reference, twice R, twice R. So V reference twice R twice R. What do you need to find out? You need to find out the equivalent voltage across this here, right? So across the twice R resistance, 2R resistance. So we can write down this one VTH, or this one V reference into 2R divided by 2R plus 1. Just simple voltage divider rule. Just simple a voltage divider rule. The voltage we divide because they are the two resistors are connected in series. We have to apply the voltage divider rule. Input voltage multiplied with this resistance divided by the total resistors. Input voltage is my V reference voltage multiplied with this resistance divided by total resistance. So it will give you V reference by 2. Right? V reference by 2. What about the RTH? RTH, to get the RTH, we need to make it short, only twice R parallel twice R. So RTH will be twice R parallel twice R raised to R. Okay. So this is for this portion, right? So now I can remove this portion here. For that particular portion, we found this one, the reference by 2 by R. Right? So now R plus R in series, so it will become what? Twice R. Now you have to look for this box. If I make another color, I'm sorry. You have to find out across this resistor. So now you have to apply again. So now my voltage is how much? The reference by 2. Twice R. We have to find out across this one. Apply the voltage divider rule. So now instead of V reference by 2, V reference, we have V reference by 2. So we get how much? VTH? V reference by 4. And what is the equivalent resistance? It's still R2 are in parallel. It is R. So we can now remove this one. It becomes V reference by 4. And we get our resistance R. So now we move to the next stage. In the next stage, again, these two are in series. We can write down this is just simply twice R. Now finally we can see from this portion, right? So again, now it is V reference by 4. And this twice R and twice R. Same. So my Thevenin voltage will be now V reference by 4 here. So finally it will be V reference by 8 RTGC. So as I mentioned at the beginning, how many number of bits are there? The Thevenin's equivalent resistance RTH is always equal to R. But we can still count it. And we can see that the statement was true. Now, from here, what we got? If we have 1 in the LSB, my Thevenin's equivalent voltage at here will be V reference over 8. So if you have only one logic 1 at LSB, all other bits are 0, then my Thevenin's equivalent voltage or the voltage across this node will be V reference over R, 80. Okay? Clear? Any confusion? Okay. So this is for 0, 0, 1. What about for 0, 1, 0? Let me draw again. We have this resistance twice R. Then we have something this way. This one. Right? This is twice R. This is twice R. This is twice R. This is twice R. This is R. This is R. According to my bit, B0 is now grounded. So B0 is my grounded. B2 is also grounded. B2 is grounded. Only we have connection to the B2. This is my B reference, right? So it is connected. Because we have to give logic 1 to B1. This is B0, B1, B2, right? Okay? So this is the connection. Now again you have to find out the equivalent Thevenin voltage and the Thevenin resistance, right? And finally we need to reach here. We saw whenever we have 0, 0, 1, we got this equation. VTH equals to V reference over 8 and RTH equals to R. Now we need to find out same for 0, 1, 0. So if you want to see here, as we don't have any reference voltage here, we just have reference voltage here. But until here, what we can see, these two are and two are in parallel. If you look at here, from here to here is ground, from here to here ground. So these two resistors are in parallel. So if they are in resistors in parallel, they have become only R. Now these two resistors are in series, though they will become 2R. So this is the first thing we already got. Now we will get our Thevenin voltage here. So starting from this is my V reference. So this is the V reference. So you have to find out the voltage drop across these two are. So V reference times now again this is my V reference time twice R divided by twice R by twice R. So we'll get V reference by 2 and RT equals to R. So we got V reference by 2. So we already have reached here. So if I just remove this portion, we saw that we got V reference by 2 and the resistors R. These are and these are in series. So we can remove one of the resistors. This is twice R. Now you have to look for this one from here. So now it will be reference by 2. So you have to put V reference by 2 here. So it will give you V reference by 4. And still RTH equals to R. So we already reach here. So it will be finally V reference by 4 times R. So for 0, 1, 0, or we can say if B1 is only B1 is connected to the reference board, all other bits are connected to 0 or logical 0, it will give you the reference over 4. And RTH is still R. Finally, if we have only B2 equals to 1, the MSB bit is logical 1 and B0 and B1 is 0. So we need to just calculate from the very beginning to here because all the reference voltages are connected to ground. So here twice R, then R, then R, twice R, twice R, twice R. It was B0, B1, B2. So my B2 is 1, so it will connect it to the reference voltage. It will connect to the reference voltage, 3 reference, and these two are grounded. As these two are grounded, here we have twice R, twice R, twice R, twice R. This is R, this is R. We are looking from here, trying to find out the Thevenin's equivalent voltage and the resistance. So these two have no voltages, so we will not get any output voltage here. What we need to find out? Only the equivalent resistance here. Twice R and twice R parallel will become R and R in series, it will give you 2R, twice R in parallel because this is also ground, so it will give you R, and now this R and R in series, it will give you twice R. So it is V reference, so you can draw the reference voltage here, V reference. Now we can calculate the Thevenin's voltage, equivalent voltage. So we just put V reference by, so it will give you V reference by 2. So here for the LSB we got V reference by 8. For this one we got V reference by 4. This one we got V reference by 2.
What if it is 1?
So, okay, I'm coming to that point. So this is for only one bit, right, at a time. As I mentioned, what you need to do, if we have more than ones, then we have to apply superposition theorem to get the final output. Not output voltage, equivalent Thevenin voltage. So for example, if we have 1, 0, 1. So 1, 0, 1, 1 in MSB, 1 is LSB. It will be V reference by 2 plus 0 plus V reference by 8. Right? Sorry, how much it will be? 5 by 8. If you have 1, 1, 1, full scale output voltage. So just V reference by 2, V reference by 4, V reference by 8. So it will be 7, V reference by over 8. So this is the full scale output voltage. So if you just put the value of V reference from our previous example, for the binary weighted we choose V reference equals to 5 volt, right? So it was how much? 35 by 8, same. So we can find out the full scale output voltage. So in the exam, maybe I'll ask you to just design the circuit. You have to design the circuit. Then you have to find out the full scale output voltage. Or I will give you some input code. You have to find out the equivalent output. For example, let's see. So, what is the general equation? General equation for this equivalent voltage, Thevenin's equivalent voltage, we can write down V ref times V over 8 plus V1 over 4 plus V2 over, this is by MSB, this is LSB. Right? This is for 3 bit. For n bit, we can write down for n bit, this is for 3 bit. For n bit, we can write down V0 to 1 to the power n, V1 to the power n minus 1, V2 to the power n minus 2, like this Vn minus 2 to the power 2, Vn minus 1 equals to 2 to the power 1. So this is the general equation. So now what will be my output voltage? In the output voltage, so that means we reach here, we reach already here. This is my output voltage, this is my RF. We have some reference voltage here, we have some resistors here, right? This is a circuit, right? This is my V reference, this is my that Thevenin's equivalent resistance, this one. And you have to find out the output voltage. The output voltage will be V naught is equals to, as we are giving to the inverting terminal, so it will be minus RF over R, this is the gain, times here the reference. Right? This is the gain, right? RF over R. So it will be your output voltage. Then here, of course, we can write down like this: RF over R V ref. Then all the bits V0 by 2 to the power n minus 1 to the power n minus 2, something like that. So we can express this final equation like this. V naught equals to minus the reference times RF by R I equals to 0 to n minus 1 bi to the power n minus I. Okay, let's try to do one example. RF is given 2 kilo ohm, R is given 1 kilo ohm, the reference is given 5 volt, and input code is equals to 101100. Find the full scale output voltage. Full scale output voltage or FSO. Find the equivalent output voltage. For the given code. So the problem will become like this. Maybe in addition, I will ask you to draw the circuit. So here how many bits? 1, 2, 3, 4, 5, 6 bits. So you have to design the 6 bits. Then we have to find out the full scale output voltage. What does it mean? Whenever we have all ones, then what will be our output voltage? And the third one is find the equivalent output voltage for this given load. So if I draw the circuit, if I draw the circuit here, so it is 6 feet. So this is the circuit. Okay. So what will be the FSO? Here we know the reference is given. How much? 5 volt. RF is given 2 kilo ohm. R is given 1 kilo ohm. And here given for the full scale output voltage, you have to consider for each position, right? So for each position, we can write down here 1 over 2 to the power 6, 1 over 2 to the power 5, 1 over 2 to the power 4, 1 over 2 to the power 3, 1 over 2 to the power 2, 1 over 2 to the power n. 1, 2, 3, 4, 5, 6 bits. So here it will be minus 10 volt times, if we take this one will be 64, 63 over 64. Then it will give you minus 9.884375. This is the full scale output voltage. Now if you have to find the equivalent output voltage for this one, right? So this is B0, B1, B2, B3, B4, B5. So you can see only B5, B3 and B2 are connected to the reference voltage, right? So which one will be connected? This one, then this one, and this one, right? So this will be 0. Sorry, this will be 0. This will be 0. So we'll have 1 over 2 to the power 6 plus 1 over 2 to the power 4 plus 1 over 2 to the power 3. So if you calculate, it will give you around
6.8.
minus 10. Yes, sir?
Minus
6.875.
Yeah. Is 11 over 16. So it is 6.875. So this is my equivalent output voltage for this code 101100. Okay. What is the resolution of this circuit? We can know the resolution of the step size equation. Step size or resolution equals to FSO over 2 to the power n minus 1. What is my FSO? Minus 9.884375 divided by 63, right? 2 to the power 6 minus 1 will be 63. It will be 0.135 or 156. 156. So this is the step size. The minimum 1 LSB. For every bit change, then we change in output voltage by 0.156 volt. So that's it from my side. So we already done with the DAC. We have done the ADC. We talked about the sampling theorems. In next class, we will start about that some characteristics of the IC, because we want to focus on them next week. The RTL, TTL, DTL circuit. So to talk about those things, at first we need to discuss about what is fan in, what is fan out, what is the propagation delay, what is the power dissipation. Then we move forward the circuit for the RTL and DTL. Because whenever we already saw, whatever you want to design, multiplexer, demultiplexer, the parity bit generator circuit, everything depends on what? Logic gates. And those logic gates actually designed by either diode or the transistor or the resistor transistor or transistor. Nowadays we just only use the transistor TTL, but we will start from the very basic RTL, then we move for DTL, then we go for TTL. And that will be the syllabus for our next exam. The sampling, ADC, DAC, and those RTL TTL. We'll see for the exam after coming back from the spring break. So after spring break, we'll continue our lecture first week, then we'll go for the exam. So that will be around 10, 11 or 12 of April. Thank you so much. If you don't receive your exam kit, please come to me. If you want to talk, we can talk at office. You can come to our office anytime. Everybody sign it?